Okay, we're going to get started here. I had offered to talk a little bit about the assignment for this course just to get started because it is due soon. So the assignment, the first assignment in this course consists of a set of pieces that go over elements related to the past few lectures, including this lecture. The first problem here is asking you to produce a causal loop diagram. This is an expansion on the take-home exercise that many of you started for this class, and it can be an elaboration on that diagram based on some of the principles that I talked about following your attempt to put together that diagram last time. What I'm looking for here is to have a diagram that has a certain amount of richness to it. I give some suggestions for sort of what's being sought in terms of the particulars of the diagram. I'm hoping that you could create a diagram that is somewhat more than 3 or 4 different variables. Might have somewhere upwards of 5. But the most important thing is that it be fairly well thought through, that it have good naming, that each variable be associated with a polarity that's clear. So you want to have a variable for, say, ethnicity, which says that, because it doesn't really have a sense of more or less. It should be something where you've labeled the loops. You're going to be asked to draw polarities for the loops, where the loop polarity indicates for a loop, which represents a feedback, whether it's a positive or negative feedback. Okay, the direction of the loop would go in the direction of the arrows in the loop itself, or the direction of the label. The label for the causal loop should go in the direction of the links that make up that loop. So if we have a loop here from A to B to C to D, and we add something like lengths going from A to B and B to C and C to D and D to A, this being a feedback loop, we would have a label for it that went in the same direction, in this case, clockwise direction. And so this might be a reinforcing feedback. You may use for this diagram either a notation we talked about for link polarity. You may either use a plus-minus convention, where plus means in a link from A to B, a plus associated with that link means if A increases, B will tend to increase, all other things being equal compared to the value it otherwise would have held. So we could do it with plus and minus, or we can do it with same and other. We talked about that last time. We could have indicate that as A increases, B tends to increase compared to the value it otherwise would have had, all other things being equal, or it goes in the other direction. It's reduced from that direction. And the loops would have polarities associated with them, which would be labeled plus and minus, depending on whether it's a reinforcing feedback plus or a balancing feedback minus. Okay. So that was problem 1. And what you're handing in there is your diagram. And I think for neatness, it's best if it be done through any logic. If you wish to draw it out with another package, I'm not going to get in the way of that. I think that's fine. Okay. Package Vensim is very good for creating these causal loops in ways that look even nicer than in any logic. And you may want to use draw.io or Google Draw or whatever if you prefer. That's okay. Okay. Any questions for problem 1? Yes.
Do you want us to submit a screenshot of the state chart, or do you want the entire package?
So screenshot is fine. screenshot would be fine, because it's not important that it be runnable, and the details of the implementation, therefore, to the degree there is one, are immaterial. So you can turn in a screenshot of it. In this case, it doesn't really hide any information of substance. Yeah.
You said it's only 5 to 6 variables?
Well, at least, I said.
Oh, okay.
I'm hoping for at least 5 or 6 variables within it. But as I say, what's most important is that it be well thought through. That you've thought it through a bit. It's been thoughtfully done. You've used concepts and names that are clear. I would be particularly cautious about making sure that if you have links between variables where it's highly ambiguous what you mean by that link, you consider putting intermediate variables in there that may not be observable. We may not be able to directly see them, but that's never a barrier for causal loop diagrams, but are sort of helping me understand what you're thinking about that link. What are you characterizing with that link? What do you have in mind, in short? That would be good to have there. And often student diagrams don't do that, and they have kind of very blunt description of A and B and their impacts, and that's not so good. So if it's poverty and violence, you want to say a little bit more about why you think there's a causal relationship there. What is it you're thinking about in particular is positing as being the case that might lead to causation there? And what do you mean by violence? You mean exposure to violence or propensity to violence? These are things that you can make clearer with a causal diagramming, with good labeling and with putting in extra variables. So it suggests that you sometimes realize that more variables do actually better explicate, better make clear what you're trying to characterize. Other questions on problem 1? Okay, problem 2, graphical integration. What I'm asking you to do here is to reason through the behavior of a stock in response to a single inflow and a single outflow. And I have various cases where I'm asking you to do that. So, if we have an inflow to the stock that looks like this, and an outflow that goes down like that, what would the value of the stock do over time? So if we have a stock that has an inflow and an outflow, it starts at a specified initial value, $20, say. And then we have flows into and out of it as given here. Well, how will that stock change over time? I want you to think that through. Now, if you want to do it by hand, I'm okay with that. If you want to do it in any ledger, I'm okay with that. If you want to do it in Maple, I'm fine with that. If you want to do it in another package, I'm also okay with that. I really want you just thinking about it. What are you going to turn in here? What you're going to turn in is the graphs of the value of that stock over time. Now, when you turn those in, as I said, they can be created in any package, including by hand. But just be sure they're labeled so that you have time on the x-axis. We're showing the value of the stock over time. And the value of the stock would be on the y-axis to make sure there's some labels for that, 10, 20, 30, whatever it is, 100. So be sure to put those in. If you want to use graph paper with squares on it, that's great. That may simplify some drawing of this grid if you're doing it by hand. I'm really not particular about how you do this. What I do want you to be doing is to be thinking through what results when we have something like this. How will a stock change as a result? And I'm not doing this for no reason. I'm doing it because it turns out that many studies in carefully controlled experimental conditions have revealed that even very technical individuals often find it very hard to intuitively specify sort of what a stock will do in response to this. We as humans are very good at certain tasks, certain types of visual pattern recognition, for example. We're not terribly good at looking at something like this and immediately seeing how the stock will behave. I want you to think that through, and I want you to develop some intuitions of how you can cross-check yourself. For example, I'll give you a hint, when these lines cross, there will be something happening with that stock that is pretty well defined. And you can develop intuition in terms of how the stock will change by reference to points like this. I also want you to be able to compare, when you think this through, compare features of the stock, like when it's at its maximum, when it's at its minimum, when it's increasing the fastest, when it's decreasing the fastest, when it's stable. How does that relate to things on this diagram? The features on the diagram involving the inflows and the outflows. They're going to be related to that. And in some cases, they'll be at a distance from it. They won't be have a direct analog. So I want you to think that through, because stocks and flows are different things. There's a semantics to them, a meaning of them. And what I'm showing here is the flows, and I want you to tell me what that means in terms of the value of the stock, okay? So for each of these, I'm looking for a value of the stock that you're going to turn in. Yeah, okay. Okay, here we're going to be talking about a series of coupled stocks and flows, okay? These are going to be first order delays here, okay? So we're going to be talking, today's lecture is about first order delays and hazard rates and understanding them. We actually introduced them last time, okay? So we're going to be representing these first order delays in two different ways. One way we introduced last time, where you have an inflow and outflow. Another way is where you have a single inflow, and you have something governing it in terms of the values of the stock, governing the rate of that inflow. And here, there's a stock that's characterizing the perceived value of a given quantity P, and another one that's actually representing the quantity that is being perceived in the population. Maybe it's the position of your car on the road or what have you. And here you are looking at something which involves an action delay to change, like the location of the car to the steering wheel, for example, and sometimes to change the perception of that. Okay, and I'm asking you to work through this example, to build it up here, and then I'm asking you to go through a couple of scenarios where you are trying out different values, and I'm asking you to answer some questions with respect to them, okay? You'll notice that I'm asking you for the different questions for slightly different things. For example, I'm asking general questions about, for your reasoning here, I'm asking here to record some results. Here I'm asking, commenting on the results and recording the results, etc. So for each one, I try to indicate what's expected from you. And then I walk you through some additional records, some additional requests where you add things in to make it a little bit more, to sort of add some noise into the system here, okay? And that's going to help some appreciation, hopefully, of the stabilizing nature of this system, even in the context of noise, okay? So I've asked you to follow those through. If you see for a given subpart that there's nothing required specifically. For example, part I here just says, please hand in your model from the above. But there may be some cases where there's nothing for you to hand in. For example, add in a parameter, right? You're not handing in something specifically for that. For A, for B here, you're not actually adding something in. Rather, you're undertaking an action. However, for F here, for each of these subparts, you in fact are delivering something. So, you know, if I'm not asking you to turn something in for a part, you needn't do so. This is just sort of a step where you undertake action. So E, there's nothing for you to turn in other than the final model, which is being built here. Is that okay? Okay, let's talk about problem 4. For problem 4, I'm asking you to go through a building up of a model. And this model is, in fact, also a first-order delay. It's a delay associated with a transition of a stock from a sort of prevalent cases to a situation where people have recovered. So there's some delay associated with recovery. And I'm asking you to experiment with this and to reason through about key values. For example, what is the value of a parameter at which the stock is no longer changing? The prevalent cases stock no longer changes. Prevalent cases is a flow into it and then a flow out of it to recovery. What's that value of a parameter for the duration of disease where prevalent cases is sort of is constant? And how does that vary for an inflow I that, you know, could be any number greater than 0, and then how does it vary with 0? Okay, and I'm asking you to perform some derivations here, which are going to be based on the definition of a first order delay. Okay, we're going to be talking all day today about first order delays and associated hazard rates. Any questions about this one? Any residual questions about this problem set? No? Okay. Not hearing any questions, then I'm going to launch into our focus for today. Okay. Here we go. Today, ladies and gentlemen, we're going to be talking through first order delays. I'm going to be reminding you about some features that we learned last time that focus on stocks and first order delays. And then we're going to go into some of the mathematics, which is going to be very important for you to understand in terms of your reasoning through some of the examples within system dynamics, okay? This is going to involve some mathematics. It will also involve some intuition, and we're going to try to be mixing them through here today, so that you're developing both. Appreciation for both. So today's focus is understanding hazard rates, which represent sort of a chance per unit time of transitioning from one stock to the other in this case. Later we'll see them for agent-based models with state charts. And then we're going to talk about first order delays as a construct that include them. So I want to remind us what we saw last time about stocks and flows. Remember that in system dynamics, we build up diagrams and indeed characterizations of models using stocks and flows. Stocks represent the state of the system. They represent sort of the current situation in the system. And they represent accumulations. They have some initial value at the start of the simulation, but after that, their evolution is governed by flows. They change after the initial time. How they change over time is purely dictated by the flows into and out. In fact, by the net flow. Flows capture the occurrence of changes in the system. Stocks represent the current situation. Flows represent rate of change to that situation over time. And if we have a given stock, how quickly that stock is changing and whether it's changing quickly up or down, the rate of change of that stock, positive or negative, is given by the net flow into the stock. And specifically, it's dictated, the derivative of that stock, quickly it's changing per unit time, is given by the sum of the inflows minus the sum of the outflows. Why the minus? Because the outflows are out from that stock. The inflows are in, so it's the sum of the positive inflows considered as positive quantities and minus outflows, right? Stock will be rising when the inflow is greater than the outflow. Does that make sense, right? You have your bathtub and water is coming in at 10 liters per minute and it's leaving at 5 liters per minute. That bathtub is going to rise, right? Hello? No? Yeah, okay. Stock will be falling when the inflow is less than the outflow, right? If water's draining faster than it's coming in, it's draining at 10 liters per minute, it's coming in at 5 liters per minute, the bathtub will be going down, right? It's draining out faster than it's coming in. And oh my gosh, that's horrible. Will be, what do I have to fill in here? Will be what? Yeah, constant or static or in stasis. It will be have a fixed value when inflows equals outflows, right? It won't be going up, it won't be going down. It'll be steady. However you want to put it, its value won't be changing over time. Okay? It's going to hold a constant value. Are we clear on this? Yeah, okay. Now, last time we went beyond stocks and flows to talk about first order delays. And the idea with the first order delay, ladies and gentlemen, was that a stock with an inflow and outflow is considered a first order delay when the rate of the outflow depends linearly on the value of the stock. So let me just make sure that notion is clear, because we did this last time together, but I didn't emphasize the general principle as much as I could have. So here's our inflow, I'll label it I, and here's our outflow, I'll label it F, okay? And suppose we have some parameter here that's a probability per unit time of someone leaving the stock. Let's call the stock X. This parameter here, alpha, is a probability per unit time that someone will leave the stock X. What would the formula be for F if it depends linearly on the value of the stock? I'll tell you F depends on alpha and X. When I say it depends linearly, give me a linear formula. Sorry? Okay, that's good. And what makes it linear there, it's linear with an offset, is that you have the M times X. So in this case, it's alpha times X, okay? We had this last time. And we see it in two ways. This is a chance per unit time of leaving X. Alternatively, you could have here a flow out. Just as well, we could have written the same one. Here we are, I inflow and the outflow of F. And we could have written this in terms of a tau, a sort of mean time in that stock. And the formula here would then be X over tau. Okay, tau is just 1 over alpha. Why do I say that? Well, if tau is 1 over alpha, and you have x over tau, then this is equal to x times alpha, right? Or conversely, if alpha is 1 over tau, then alpha times x is just x over tau. You can go back and forth between these. You can talk about a mean time in the stock and number of time units, or you can talk a chance per unit time of leaving the stock. And units 1 over time, per unit time. So probability per unit time. Okay? We could phrase this first order delay either way. But the key point is that the outflow, that depends linearly in the sense it's just a constant times the value of the stock out of which it's flowing. Do you see that? This is just some constant, alpha, times the value of the stock, x. Now, the bigger x gets, what does that mean about the outflow? The bigger x gets, the what? How does that change the outflow?
The outflow gets bigger as well.
The outflow gets bigger as well. And that, come on, how does a bigger outflow affect the stock? Yeah, it's going to decrease it over time. So if we increase the stock, the outflow will increase, and that will tend to pull down the stock. Does that sound like a certain type of feedback? We increase A, it leads to a series of changes that push back against that original change. What sort of feedback is that? It's a balancing feedback. It's a balancing feedback. So first order delay contains a balancing feedback. Where is that feedback in terms of the diagram? Well, it's a feedback from the stock to the flow. That's a plus link. And that flow is an outflow, so it lowers the value of the stock. Okay? So it's the flow has, you could think of it, a negative link back to the stock. The bigger the outflow, the smaller that stock will be, all of the things being equal compared to the value it otherwise would have had. So a first order delay is associated with the balancing feedback. Now, systems that have balancing feedbacks in them, when we have a balancing feedback, when we consider it in isolation, what sort of behavior do we expect from that? Do we expect it to blow up? No. What do we expect? Stability. It sort of pulls back to an equilibrium. It's in stasis, it's like homeostasis. It's like our bodies keeping us appropriately hydrated with sufficient amounts of food, and good temperature. Our bodies, through these feedbacks, make sure that they're kept in this sort of equilibrium. And when we go out of it, it's at our peril. Like we have a fever, right? Get extremely famished. So, ladies and gentlemen, we have a system which tends towards equilibrium. If the value of that stock is above its equilibrium value, what's going to happen? Why does it want to go back to equilibrium? We talked through it last time with a running example, but I just want to make sure the intuitions stick in. If the value of that stock is above its natural value, what's going to happen? Value of the stock is above its kind of natural equilibrium. What's going to happen as a result? Okay, why will it drop to its equilibrium? Because what? Let's go through it mechanistically. The value of the stock is far above its natural value. What's going to be the result of that going to be? Sorry? Yeah, the outflow will be much larger. The outflow will be bigger than the inflow, because remember, at its equilibrium, what is going to equal what? Inflow equals outflow. Above its equilibrium, if the value of the stock is above its equilibrium, the outflow is going to be bigger, because the outflow depends linearly on the value of the stock, right? Bigger the stock, bigger the outflow. So if the stock is above its equilibrium, the outflow will be above its equilibrium. The outflow will be bigger than the inflow. After all, they're equal at the equilibrium. Now the outflow is bigger than its equilibrium value, so the outflow will be bigger than the inflow, and what will happen as a result? Stock will go down. So if you have that stock and you knock it well above its equilibrium, it will want to go back to that equilibrium. How if that stock value is too small? What's going to be going on there? If that stock value is much smaller than its equilibrium value, what's going to happen? Well, okay, but let's think why. So if the stock value is smaller than its equilibrium, the outflow will be smaller than its equilibrium value. Because remember, at its equilibrium, the two are equal. If the stock is smaller than its equilibrium, the outflow, which just depends linearly on the stock, is going to be smaller than its equilibrium value. And if the outflow is smaller than its equilibrium value, it's going to be smaller than the inflow. So what's going to happen? If the outflow is smaller than the inflow, what's going to happen to the value of the stock? It's going to rise. It's going to rise. And it's going to keep on rising until it reaches its equilibrium, at which point, what will be what? Equal to what? Inflow equals outflow. And you can knock that stock. You keep on knocking. It wants to go back. It wants to get back to its happy zone. It wants to get back to its safe space. It wants to get back to its equilibrium. And it's the natural order of it that if you perturb it, if you disturb it, if you knock it, it's going to want to go back into balance, where balance means its inflow and outflow are the same. Does that make sense? I want you to have that rock solid intuition because we are going to need to build on it many, many, many times in this course, including for the agent-based components, including potentially for the discrete event components when it comes to reason about queues and so on, and waiting times and rates of service, etc. This is a very important central intuition, okay? Okay, now we're going to talk about first-order delays and their implications, and this is others lectures. But I want to go through a bit of the essential mathematics of it. Okay? Fundamental mathematics of this do involve calculus, okay? So suppose we have a stock X, and we have some chance per unit time of developing diabetes, okay? Alpha. This alpha is what's called a hazard rate, chance per unit time. It's not a probability. It can be bigger than 1. It can't be smaller than 0, but it can be bigger than 1 because it's a probability per unit time. Say probability per year. In the health sciences, they'll call these things, for example, incidence rate or hazard rates. It's per unit time likelihood, okay, per unit time probability, okay? And if we consider the stock of people, and yeah, there's a bit of a disjunction here. This says diabetes, but it's actually, you could consider it for the sake of this slide. I need to correct this, but it's actually mortality rate, okay? So alpha is a per unit time mortality rate. It's a probably per unit time that someone will die. Now, if we consider a small delta t, remember, alpha here is not itself a probability. It can be bigger than 1. It's probably per unit time. Let's consider, so let's suppose it's 1% per year mortality rate. It's 1% per year, okay? Now let's consider some small amount of time. Let's say 1/10 of a year. The fraction of the population that will die within that tenths of a year, the probability that someone would die would be 0.01. That's alpha. That's the hazard rate. 1% times the amount of time, 0.1. Okay, so it'll be 0.01 times 0.1 or 0.001. Okay, the idea that we have here with the stock is that if we have a very small amount of time, dt, and we're going to consider the rate of the flow as just being the value of the stock times that probability. Okay, so that's the flow rate. How many people per unit time are going down? So if we have 1,000 people and we have a 10% chance per year of dying, the rate of which people are dying is 1,000 times 0.01. Sorry, I said 1% chance of dying, 1,000 people. Then we have a number of people per year dying of 1,000 times 0.01. That's the 1%, which is 10 people per year. Does that make sense? Does that make sense? If there's a chance per year of X, excuse me, of alpha of someone dying, and we have a value of the stock of X, chance per year of dying of alpha, then the number of people dying per year is X times alpha. So you have a 1% chance of dying out of 1,000 people. It's 1,000 times 1%, or 10 people per year on average. Does that make sense? Just trying to bring you along with this. Okay. Now, if we consider a very small unit of time, ladies and gentlemen, and we consider like over 1/10 of a year, how many people die over the 1/10 of a year? Well, we have 1,000 people, and we have 1% chance per year, and we have dt equal 0.1, then on average over 1/10 of a year, 1 person per year dies. Over the entire year, on average, 10 people per year, 1,000 times 0.01. Over 1/10 of a year, it's 1,000 times 0.01 times 0.1, or 1 person per year. Does that make sense? Yes? Okay. Okay. Now, when people die here, they flow out, right? They flow out of here. They're flowing out. There's a rate of change that's drawing down X, right? We have 1,000 people in the stock, and per capita rate of transition of 1%, the rate of flow out is going to be 10, and flowing out is going to draw down the stock, okay? And the key thing here, ladies and gentlemen, that I need you to realize, I want you to come back to this again and again in your thinking is, if I run this, if I start with a value of 1,000 and I run this for 1 year, 2 years, 3 years, and there's no inflow to that stock, what's going to be the value of that stock going to be doing over time? Sorry? Okay, so there's an intuition there we're going to work on. It turns out it's going to be going down a lot over 1,000 years, over 100 years. 1% chance per year, each person leaving, 1,000 people here. Is the value of the stock going to be going up or down? Down. It can only go down or stay the same, right? I mean, there's no inflow. And it's going to be going down. And as it goes down, what else is going to go down? The number of people per unit time leaving, right? Each year, students get a little bit confused about this sometimes on an exam, because they're thinking, wait, it's going down at 10 people per year. But is it going down at 10 people per year each successive year? No, it's going down slower as the size of the stock drops, isn't it? The rate of outflow, people per year dying, is going down. Because if there's only 500 people in there, after some number of years, how many people per year are going to be dying? 5 per year now. As the stock goes down, the value of the outflow goes down. Does that make sense? Yeah, so we have this coupled system. This is part of the feedback, right? The stock is high, the value of the outflow is high, we'll draw it down faster. If the stock is low, the value of the outflow will be smaller, we'll draw it down less quickly. Okay. So, ladies and gentlemen, here we're going to have a rate of change given by, for this outflow, of alpha times X. I want to talk about how this works out over time. Let's consider a stock which starts with a single person in it. Okay? And we're going to be asking, what's the probability that that person remains in the stock after a certain amount of time? I want to talk about this notion of a hazard rate, because it's not a probability, it's a probability per unit time, and I want to develop your intuitions about it, because it'll be important for understanding later parts of this course as well. Okay, now let's imagine that we have some time here that's between, and I thought I had edited this, but I will do so now. It's time, ladies and gentlemen, here of time t. Okay, it's not just one; it's t. I decided to generalize this so that you could understand another feature which will be coming up. Okay, so imagine you have a hazard rate, a probability per unit time of alpha. Now let's consider that we have an entire interval from 0 to t, so it's a blank t. And then I ask, okay, if you have only one shot at it, you have this certain hazard rate per unit time of alpha. In order to turn that into a probability, I need to multiply it times the length of time. It's probability per unit time, so I need to multiply it by time to get a probability, okay? I'm imagining the situation where we're only considering one shot at the game. It turns out we're going to be refining that a lot. So this is a simplified argument leading to something more sophisticated. So the probability here is alpha times t. We imagine t is small, and so we have a probability of leaving of alpha times t. And now I want to ask, what's the probability of not transitioning over this time? Anyone? 1 minus that, right? Probability that I left in that time t is alpha times t. Probability that I don't leave in that time t is 1 minus alpha times t. Are we okay with that? Probably I'm still in that stock. I'm still in the stock. I haven't left after time t. Given that I have a hazard rate alpha leaving here, the probability, the number of people per unit time leaving is alpha x. Probability that I'll remain in there is 1 minus alpha times time t. Now here we're considering we only have one chance, one shot at leaving over that entire time. In fact, with hazard rates, you have ongoing chances. And I want to walk you through this so you can develop the intuition of the math that comes out. Now imagine we don't just have one shot over that entire time too. We have 2 chances as part of that. So in the first little bit, from 0 to t over 2, we have a probability of leaving. And then if we haven't, conditional that we haven't gone already, we have a chance of making it in the next half, from t over 2 to t, okay? So imagine we have 2 chances across this time t. So the probability of transitioning over the interval of length t over 2 is, well, it's a hazard rate. To get a probability, we multiply the hazard rate times a what? Times the
interval.
Yeah, the length of the interval, which is the length of time. Okay? This is, ladies and gentlemen, the hazard rate is probability per unit time. So to get a probability, you multiply it by time. It's just like if you earn a certain salary per month, to get how much salary you earned, you need to multiply it by the number of months that you were working. That gives you dollars. Does that make sense? If you have a rate of flow into a bathtub of 10 liters per minute, and you want to know how much water has come in recently, you say, okay, over the past 5 minutes, how much water has come in? It's 10 liters a minute in times 5 minutes, or 50 liters have come in. Right? So we have the units of the hazard rate being probability per unit time. To get a probability, we need to multiply it times some time. So that becomes a probability. The time cancels, and the time cancels the unit time and the time in the denominator there, and we get out a probability. So the probability of transitioning over an interval of length t over 2, if t is small, it's alpha times t over 2. Does that make sense? This is what a hazard rate gives us. It's a probability per unit time. if we have a small amount of time, delta t, and we have this hazard rate of alpha, the chance of leaving the next little bit is alpha times, and this next little delta t is alpha times delta t. So here it's alpha times t over 2, or alpha t over 2. And the probability of not transitioning in this length t over 2, that first little bit here, is 1 minus this, right? This is just the probability of leaving alpha times t over 2. The probability of leaving that first little bit between 0 and t over 2. And the probability of not having left is 1 minus alpha times this, right? Alpha times t over 2. The probability of going in that time, the probability of not going is just 1 minus the probability of going. Does that make sense? Okay, now, that is the key building block that we're going to draw on here then. Now we're going to reason about the whole interval, okay? Ladies and gentlemen, so we have this interval here between 0 and t. And because it is important for my argument here, I am going to take the odd step here, admittedly odd, but I think important, and I'm willing to do it. I am going to label this here just so it's very clear what I'm talking about. That is t, and in the middle here is t over 2, right? Here we go. I told you the lectures would be hands-on. Okay, there we go, and back here, of course, is 0. Okay, so here we have time 0 through time t broken up into 2 steps, right? There we go. Okay. So if we want to consider now, what's the probability that we will remain in this state after time t? How are we going to figure that out? What would, if we were to ask, what's the probability we will not have transitioned over time t? How would we need to figure that out? Anyone? In order to not transition over time t, what do I have to do in each of those intervals? Think about it. Think about it. Okay, I want to figure out what's the probability that I don't transition across this entire time t. In order for me to not have transitioned across this entire time t, what do I need to have done in the first interval? Not transition. What do I need to have done in the second interval? Not transition. And it turns out that conditional on me not having transition yet, the chance of me transition in the second interval is independent of the transition, the chance that I transition the first, conditioned on me still being in there. So the probability of remaining in that state, ladies and gentlemen, in the state without transitioning, is just the probability that I don't transition in one interval squared. I need to not transition the first times the same value for not transitioning in the second. Conditioned on me not having transitioned by time t over 2, my chance of not transitioning between t over 2 and t, if I haven't transitioned yet, my chance of not transitioning between t over 2 and t is also 1 minus alpha t over 2. It's a chance I won't transition, that I remain in my state. The chance that I do transition during time t over 2 is alpha times t over 2, right? Right? So the chance that I won't is 1 minus that. So up here, I have to not transition the first. I have to dodge that bullet, and then I have to dodge this next bullet as well, that I don't transition the second. So what's my probability of dodging both those bullets? Well, it's just the square of the probability that it's just the square of this probability that I dodge the first and dodge the second, that I dodge the first, okay? So here, ladies and gentlemen, we have a probability of not having transitioned over both intervals and over the entire time t of 1 minus alpha t over 2 quantity squared. Have you seen this before in probability class? You probably have encountered this notion before here, right? Right? Okay, if I'm going to, avoid dying in the next 2 years, what's the probability that I avoid dying in the next 2 years? Well, what's the probability I avoid dying in the first year? And probability I avoid dying in the second year, conditional that I haven't yet died by the end of the first year, and multiply those probabilities. So, if you're not feeling confident about this, you can study this more, but you'll have to reason it through that if we have an entire interval t, and we have a chance of leaving the first interval, chance of leaving the second interval, the only way I could not have left over time t is if I didn't leave in the first and I didn't leave in the second, and those two are independent, conditional on me having not left in the first interval. My chance of leaving in that next little interval is the same as it was of leaving in the first interval. So we get this 1 minus alpha t over 2, alpha times t over 2. Okay, squared. Now, suppose we have three such intervals. How would this change? Can anyone tell me? Sorry?
The power.
Okay, the power would change, because now I've got to dodge the bullet 3 times, right? I got to dodge it, right? And I have to dodge it all 3 times. What else changes? Yeah, it's t over 3. Because each time I'm dodging over a smaller interval. It's actually easier to dodge it, right? I don't have to duck quite as much. So it would be 1 minus alpha t over 3 to the 3rd power. What if it were n intervals? What if this were divided up into n intervals? What would this be? How would that formula be different if it were n intervals? So here's with 3. What if it were n intervals? Yeah, okay. So the probability of remaining in the state is then 1 minus alpha t over n, and then to the nth power. Does that look at all familiar to anyone? Let's suppose that we took the limit of this as n goes to infinity. So we considered a larger and larger number of the intervals, like this kick of the can for smaller and smaller bits of time. It's not just limited to 1 chance over this entire time t. It's not just limited to 2 chances over t. It's not just limited to 3. I actually kicks at the can on a constant basis. I have these little intervals where I also have a certain risk of leaving, but that risk is small because it's a small bit of time. My probability per unit time of leaving is, say, 0.01 per year, and now we're considering the level of seconds my chance of leaving. It's a very, very small chance I'll leave in that second. And we're considering as n goes to infinity, as a smaller and smaller intervals, microseconds, and so on. This is the probability that I remain, that I haven't left yet. Does anyone recognize that? What's that? Okay. It's related to differentials. I think you've got a chance here, but it's actually not 1 because this is becoming smaller, it's true, but we're taking it to the nth power more and more time. But this is, ladies and gentlemen, there is something that this represents, and it's a beautiful thing. Okay, probably it won't convince you if I yell it too loudly, but it's beautiful. What is that? Well, it's not unrelated to the things people are saying, but do you recognize what that is? Oh man. Oh man. I'll give you a hint. If I were to write this out, I could write it as a Taylor series, and it would be 1 minus alpha t to the n plus alpha t to the n squared over 2 factorial plus da, 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 da. What is this? Yes, it's e to the minus alpha t. Ladies and gentlemen, that's what that is. This is e to the minus alpha t. A long time ago, perhaps in a galaxy far, far away, you encountered this. It's a great thing. Ladies and gentlemen, it's a beautiful thing. Maybe you heard it from me first. Take my word for it, okay? Okay, so this is e to the minus t, ladies and gentlemen. What this is telling us is if we have a certain chance for unit time, 0.01, and we have that chance for unit time, it's not that just we have one kick of the can over that amount of time t. We're having constant chance, small chance that any little bit will leave all along the way. Just like that. The probability that I remain after time t will be e to the minus alpha t. The probability that I will have left during time t is what? If this is the probability I remain after time t, e to the minus alpha t, what's the probability I will have left during that time?
1
Yes, 1 minus that is the probability that I will leave. So this is the prob left sometime during time t. And if you haven't been convinced of how beautiful this is, all you have to do is compare it with my writing. And at least you recognize it's more beautiful. True or not? Okay, ladies and gentlemen, this is the probability that we left sometime during time t. This is the probability haven't left after time t. Okay, haven't left. Okay, left after time t. Okay, now. What does that look like over time? What does this look like over time? Suppose I started at a probability of 1 of being in that state. How does this change over time? What is it at a qualitative level? What does it look like? And whilst I'm explaining this, I'd like you to call up your AnyLogics so that we can look at it with greater detail. We can marvel at the beauty. Okay, ladies and gentlemen, what does this look like on a qualitative basis? E to the minus alpha t. Suppose alpha is, 0.01, and we're examining the value of t from, t to 0 to 1,000 or something. What does this look like? Okay, it decreases exponentially, and give me an intuition of what it would mean, what it would appear like if it decreases exponentially. Okay, growth rate slows, but if alpha is 0.01, is this going to be going up or down over time? As t gets larger, is it going to be going up or down over time? Well, let me ask this. Let me bring it back to the intuition for this. If this is the probability I haven't left after time t, as t gets larger, is that going to go up or down? Down. Probability I haven't left yet, it's going to only stay the same and go down. It's never going to go up. Now, let me see if I can raise this intuition even further. E to the minus alpha t, what is this equal to? If we were to write it, we want to get rid of that minus sign. How could we, what is this equal to? It's equal to, ladies and gentlemen, if you have a minus and an exponent, what is that equal to? What is 1 divided by e to the alpha t, right? Does this one get big over time? E to the alpha t? Yeah, so this e to the minus alpha t got smaller over time because it's got something bigger and bigger in its denominator. Ladies and gentlemen, so this is gonna, as t goes up, this is gonna get smaller, but how is it gonna get smaller? Is it just gonna go down linearly like this? Like that? What's gonna happen? Yeah, it's gonna drop. Is it gonna drop faster or slower at first? Sorry?
Slower.
Slower? Okay, so we have two hypotheses. One will go like this, one will go linearly, and one will go like this. So which one do you think it is? The sort of, we'll call them A, the one that goes slow and then fast later, B, the one that goes down linearly, and C, the one that drops quickly and goes. Man, this could be a multiple choice question. I'm gonna take a picture of this. Scan. Normally the exams for this class take on the order of 45 minutes to an hour each to mark. So OpScan I wouldn't be opposed to, but I don't like doing that to my students. So is it more like A, B, or C?
C.
Okay, now why is it like C? Because the longer it's been that we've been out. So let's put it this way. Why does it drop really quickly at first? Because it's very likely we're still there to leave, actually. And the longer we go, it's very, 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 very unlikely we'll have left. Let me ask this, and this is key. Oh, man, this is key. Mark my words. Conditional on you still being in the state, not having left yet, still being in that stock. What's your chance of leaving in the next little dt? It is, speak on. Conditional on my being in state X, still being here, not having left. What's my chance of leaving in the next little dt? If I'm a single person and I have a 1% chance per unit time of leaving, in the next little dt, what's my chance of leaving?
Alpha.
Alpha times dt. Because remember, alpha by itself is not a chance. It's not a probability. So you got a probability. Just like if you have a salary, so many dollars per month, you have to multiply it by a number of months to get a salary. So it is with probabilities. If you have a probability per unit time, you have to multiply it by time. The time here is a little bit dt. So if I have a chance per unit time of leaving, that's alpha, and I have a little interval time dt, what's my chance per unit? What's my chance of leaving over that delta t? It's the alpha times delta t. Remember that? The response is less than resounding. Okay, ladies and gentlemen. You remember? Remember? So here's X people at risk. If you're talking about a single person, they have a chance. So a single person, a chance per death over a small dt is alpha times dt. Chance that I'm going to die, if I have a chance per year of dying of 0.01, chance per year, the chance that I'm going to die in the next 0.001 years. Okay, don't get too excited. Is going to be 0.01 times. So that's my chance per year of dying, times 0.001 for the amount of time over which it's applied. So, ladies and gentlemen, if I am still in the state X, and I have a chance per unit time of leaving at alpha, and I consider the next little bit dt, what's my chance of leaving during that time? I just told you. Yeah, alpha times delta t. Does it matter how long I've been in that stock? This is key. Does it matter how long I've been in that stock? No, it does not matter. It does not matter how long I've been in the stock. I have the same kick of the can for the next little bit. Conditional on still being in the stock, I have the same little chance. Then why is it that this drops so quickly at first? Because even though if you're in the stock, your chance per unit time of leaving the next little bit dt is alpha times dt. The chance that you're still in the stock is actually getting smaller and smaller, and that means that the chance that you haven't left by time t is dropping very quickly at first because you're almost certainly in the stock. It's dropping more slowly later because you're probably not in that stock. So the chance you haven't left yet is decreasing slower. If you're in the stock, you have the same chance per unit time of leaving, but you're very unlikely to be in the stock, so it's dropping slower over time. Or let's put it this way, it may be easier to think about it if we have a population of people. If we have 1,000 people here at first, we talked about it earlier, and each of them has a 0.01 chance per year of leaving, then at first we'll be leaving at 10 people per year, right? But after some number of years, we only have 500, we'll be leaving at how many people per year?
5 people per year.
5 people per year. And after a little bit longer, we have 100 people there, we'll be leaving at how many people per year? 1. So as the value of the stock goes down, the rate at which it's draining goes down as well. Remember, it's a first order delay. Value of the outflow depends directly, linearly on the value of the inflow. So as the value of the stock drops, the value of the outflow drops, which means the stock drops more slowly. Thank you. So at first it drops fast because there's lots of people there. Or at the individual level because you're almost certainly there. Later it drops slower because there's few people in the stock. So there's fewer people at risk of leaving. And if you're dealing at individual level, you're unlikely to still be in that stock. Does that make sense? But these things are hard to think about sometimes. Let's go simulate it. Shall we not? Hey, you've been watching enough of my hands-on work. Let's take some of our own. Okay, here we go. Let's go into AnyLogic. We'll have to be quick about this because the time is a ticking. I'm going to create a new model, and this will be called first order delay redux. Okay, we're revisiting this, and I'm going to make its time units years. And I'm going to say finish. I'm creating a model here, which is going to have a first order delay. And we're going to observe how these things emerge from it, okay? So here we go. Here's our model, first order delay redux. And so this is just sort of a revisiting of it. And we are going to create a stock. And that stock is going to have an outflow. And the value of the outflow will depend linearly on the value of the stock. Okay? So here we go. There's main. And we are going to go here to the palette. And we are going to drag in a stock. There we are. And this is going to be called people. And we are going to drag in a flow, which will be called death. And we are going to drag in a parameter, which will be called mortality rate. This is a hazard rate. Call them rates a lot. And there is going to be a dependence of death on 2 things. What are the 2 things on which death will depend here? the speed of that flow, the rate of that flow, on mortality rate and on what else? Yeah, and on people. If there ain't no one to die, there's going to be no death going on. If there's 0 people, there's going to be no death going on. Okay, so I've just dragged this in. Next, ladies and gentlemen, I am going to go and assign bits of information. What are the pieces of information I need to assign? For the stock, what do I need to tell it? Initial value. That's it. After that, its value is dictated by what? By the values of the flows. So the initial value here for the stock is going to be 1,000. We're going to draw on the numbers I've been spouting to you. Okay. Next, for the mortality rate, let's make it 0.01. Ladies and gentlemen, for the mortality rate, we make its default value 0.01. Turns out that with parameters, we can specify them in the properties of the scenarios of the experiments we'll run. But this will be set to a default value of 0.01. Okay. And next, we are going to go, and for the flow, what is the formula going to be? Yeah, mortality rate times people. Okay, there we go. Okay, I'm going to build it on mine. It's a happy camper. Does anyone want me to show you what more I've done? I went to the palette, I dragged in a stock, I dragged in a flow from there, make sure green is the color. I went and I dragged in a parameter, and I hitched up the parameter with a link to death and people with a link to death. This indicates visually that death depends on these two things causally. And here I put for mortality rate a default value of 0.01, and for people I gave it a initial value of 1,000. The next thing I'm going to do is I'm going to, from the palette, I'm going to drag in a time plot. We go down to the analysis area here in the palette. It looks kind of like some graphs and so on in the palette, and I'm going to drag in a time plot. And this time plot is going to here refer to, there we go, refer to, it's going to plot out. So I'll add into the plot a plot for the number of people. And so I added in a value to the plot, and the value is going to be given by people. Okay. And I want down at, well, we'll leave it as display up to 1,000, a time window of 1,000. It will update every 1 year. Okay, that will be the default. Every 1 year it will be updating. Okay, so it's recurrence time of 1 year here. Okay, so ladies and gentlemen, the final thing we're going to do before we run this is we are going to go back to the projects menu, and we will go to the simulation area, and we will set this so that it runs only for 100 years. Okay. So I'm going to say stop at specified time for the simulation, and the time at which it stops is 100 years. I'm going to save it. Build early, build often, and now let's run it. What are we expecting to see, ladies and gentlemen? What are we expecting to see here? Will the stock be totally empty after 100 years? Why or why not? Chance per unit time of leaving of 0.01, probability 0.01 times 1,000 is 10 people per year. After 100 years, wouldn't that drain the stock? Why not? Yeah, because the number of people in the stock is going to be going down. So the rate of outflow is going to be going down. So will everyone have gone from the stock after 100 years? Absolutely not. There'll actually be quite a few people there. And in fact, it turns out that the average time people spend in the stock, and this is true in general, I said it earlier, the average time they spend in the stock is just 1 over the hazard rate. The hazard rate here is 0.01, so the average time they spend in the stock is 1 over 0.01, or what? 100 years. That's because some people will take very, very long time to leave. But I've truncated it to this for the moment. And so what you see is it goes down and first goes down more quickly. Why does it go down quickly at first? Yeah, because there's lots of people there. So the number of people in the stock is going to drop quickly because there's lots of people at risk of dying. As it goes on, there's fewer and fewer people in the stock, and therefore there's fewer and fewer people at risk of dying. You notice, by the way, this is truncated to 300. If we really wanted to see it with greater clarity, and time is a ticking, I'm going to go back and change the settings of that so that the value of the graph goes from 0 up to from 0 to 1,000. Okay, and we can do it further down here. Okay, the scale here I'll set to fixed. It'll be from 0 to, okay, so this is the vertical scale, 0 to 1,000 in the properties window. And now I'll run it again. And what you'll see is there's actually quite a large fraction of the population that's remaining after time 100. How could that be? How could it be that there's quite a large fraction of the population leaving after time 100? Well, it turns out that the mathematics is such, a given person will remain in that stock after time 100 is 1 minus e to the minus alpha times t, or 1 minus, the chance that they left some time during that is 1 minus e to the minus alpha is 0.01 times t, or 100. So the probability they left some time in it is 1 minus e to the minus 1, which is not actually nearly close to 0. There's quite a few people in there still. The average time they spend in it, in fact, is going to be 1 over the mortality rate. Now, let me ask this. So each of these people, while they're in the stock, has a chance per unit time, per year, of 0.01. So, ladies and gentlemen, if I ask you for a small bit of time, let's say 0.1 of a year, what's the probability, not the probability, not the hazard rate, but the probability that someone will die within that next little 0.1 of a year? What is it, roughly speaking? It is, what is it? Okay, yes. And that will be the correct way to do it. If we're dealing with a very small delta t, 0.1 is probably good enough to have a pretty good approximation here. It's roughly speaking, it's alpha times 0.1. But it's not going to be exact at all, because there's a chance that it's not going to be that, because you're not actually subject to that entire probability for that entire time, because you may have left prior to that. So it's still an approximation, and really you should use it using the formula over there. But the point is, while they're in the stock, the probability that they will die in the next little day is going to stay the same, no matter how long they've been No matter how long you're in that stock, you have that same kick of the can for the next day, your chance of dying. No matter how old you are, you have that same chance you're going to die in the next year. Not a very good description of the human condition. After 100 years, you typically have a higher chance of dying in the next year than you would if you're, in your 20s. Mark my words. But the number of people in the stock is dropping quickly at first, slower later, because more people are leaving earlier. And why are they leaving early? Because the value of the stock is higher. As the value of the stock goes down, the number of people leaving goes down. Okay? So, ladies and gentlemen, hazard rates, first order delays here are tied together. Hazard rates like this will follow us through the entire course. They will follow us in agent-based modeling. They will follow us in discrete event modeling, and they're applicable here. A hazard rate is not associated with a probability. It's associated with a probability that's continuously applied over time. I have a certain chance of dying not just once during the year, but at each little bit of time. And it leads to, at a mathematical level, this sort of continuous drain down associated with the stock. Your average time in that stock will be 1 over that hazard rate. They go together. And I'll include some slides which show that mathematically, why they go together within this for those who are interested. Okay? So, ladies and gentlemen, hazard rates. And in a first order delay context. Okay? In your problem set, in the assignment, you are exploring a different way of framing a first order delay. We could have a inflow in here and something like this, or we could have just one inflow and have the value of the inflow depend linearly on the value of the stock. You will see that within the assignment if you haven't already done so. 2 different ways of expressing first order delays that we'll be talking a little bit more about next time. Okay, so that's all we have time for today. Thank you very much for your attention. I'm glad to answer questions on the problem set or other matters in my office hours each day after class. I will be going over, I think it's in 371 or 372 after class today. Thank you. Yeah.
The graph you made there, was that a time plot graph?
That's a time plot.
Okay, mine comes up blank. How do you link it to your actual diagram?
Okay, give me just a second while I stop the recording here, if you wouldn't mind. I'm just